So before I talk about why we don't use MSC or mean square error function as a cost function or loss function or error function in logistic regression. Okay, this is a concept. But before coming to the main concept, first I want to talk about some basic concepts. Okay. With respect to maths and with respect to graph, so that if I able to, first of all, I will try to establish this concept, then I will go to that our main question, that why MSC is not used in logistic regression. Okay. So there are some few concepts, there are some mathematical concept. The first concept is I'm giving example with respect to graph. Okay, calculus and graph. Okay. So let's suppose this is one graph. Why I'm talking about graph, I will come later. But let's suppose this is a graph. Okay, this is one it is called parabola or quadratic equation. Okay, so this graph is represented by, suppose I'm writing fx mathematically. So this can be represented by like ax square plus b, something like that. Okay, this is a quadratic equation. Okay, so this can be this graph can be represented mathematically by this equation. Okay, this is one graph. Let's suppose I have another graph, which is like this, like this, like this, like this, like this, like this. Okay. So this kind of graph, the first kind of graph, this kind of graph is called convex. There's a concept called convexity. Do you know that? Convex.
No, I don't know.
Convex. Convexity or convex. Okay. So this graph mathematically in terms of algebra or in terms of graph, this kind of graph where you can see it has a, it has a smooth kind of graph. Okay, where it has no much, it has no much, it has just one local, it has just one global minima. It is called minima, minimum point. Okay, if the graph is like this, if the graph is like this, then it will call maxima. Like suppose if I draw the graph like this, like this, so it is a maxima point. Here the maximum point. Okay.
Yes.
So this graph, you can see that this graph has just one local mix, one global minima. There will be just one minimum point at this point. Okay. And this graph, you can see this graph has, the problem with this graph is that this graph has many minima. The minimum point will be here, one will be here, one will be here, one will be here. Okay, so this small point where you find some minimum value, it is called local minimum. Okay, this point is called local minimum, because you in this graph you can find multiple local minimum value, right?
Yes.
Because you will find here also, you can find here also, here also, here also. But the minima will be, the global minima will be here. This is the lowest point, right? So this is called global minima. Global minima means the lowest in the lowest. It is called a global minima. Okay. So in this graph is not convex. This is called non-convex graph. This is not a convex graph. It is not a convex graph. So in convex graph, there will be either just one global minima or global maxima, just one minima or maxima, right?
There will be no local minima.
There will be no local minima in convex graph. This is a mathematically proved. Okay. So in the convex graph, there will be just one, it can be either global minima like this or global maxima like this.
Okay.
Just one minima or one maxima. But in the convex, there are multiple local minima. There can be multiple local small minima, and there will be one global minima. Okay. Now the problem is that you know that gradient descent, right? So in machine learning model, we use a technique. It's a process. It's not a machine learning model, by the way. A lot of people confuse. It's a process. It's a mathematical process, or you can say a technique. Okay, through which we find the minima. Okay, let's suppose for this graph. Let's suppose this parabola graph. Okay, if I ask you how to find the minimum point, right? So you can see that by looking at the graph, you can see that the minimum point at, let me give some name here. Let's suppose suppose this point is P. I'm taking the random point P, okay? So by looking at the graph, you can say that the point P has is a minimum value, right? FP, the value at P, I'm calling it FP, this will give me the minimum point. Is it correct?
Correct.
Okay, this point gave me minimum point by looking at the graph, but mathematically how to find it? So mathematically to find out, we use a process called gradient descent, okay? What if you have studied the gradient descent in machine learning, what we do, we take any point in the graph. We can start from any point. It is called initialization process. Okay. For example, in linear regression. So in linear regression, we have a cost function, right? We have a cost function. So in the cost function, we initialize as what is my theta 0, because we need to find the theta 0 and theta 1, right? The optimum value for this, where my error will be minimum. So we take any point in the graph and we initialize our weight. It is called weight in terms of machine learning. And we start drawing a tangent. Like at every point, because see, in the calculus, if you see the calculus, the minimum point, how to find the minimum point mathematically, that tangent, it is called slope. Okay, the slope will be 0 here. Okay, let's suppose this function is f. Okay, and if we draw the differentiation, I mean dy dx of f, it is called slope. Okay, if the slope becomes 0, okay, then it becomes the minimum point. This is the mathematical proof to find the minimum point. Okay, so if you really find the minimum point on this graph, you have to find that the slope is 0. I mean the tangent becomes 0. So what we do in the gradient descent, we start from any random point on the graph, and we find the tangent here, tangent. We find the slope here, multiple. We will do multiple iteration, and after multiple iteration, finally we reach a point where my slope becomes 0. Okay, and during this iteration, it can be chance that we can, after this point, we can go top, suppose from here. Okay, then ultimately, if you do iteration, it will come down here. Ultimately, it will start from here. You will find, suppose we did 1,000 iteration. Okay, so in 1,000 iteration, we found this point, which is the minimum. But maybe let's suppose instead of 1,000 iteration, you're doing 2,000 iteration. So it will again go top, and it will go, but ultimately it will come down. It is called gradient descent. I'm not going to cover that. Okay, so but the concept says that in the case of convex graph, applying the gradient descent is possible. You can easily apply this concept, this process, which is called gradient descent in the convex graph. Okay, this is a concept. You can make a concept. If the graph is convex, then we can apply gradient descent smoothly, and we can find the minima or maxima. This is the concept. Okay. Any confusion here? This point, this statement. So I'm making this statement. If your graph is convex, then applying the gradient descent is easy, and you can find the minima or maxima. Otherwise, it is become difficult. Okay. In case of non-convex graph like this, okay, here the problem with there is a one limitation with respect to gradient descent. There is one limitation. You can apply gradient descent only when your graph is convex and there is just one local minima or local maxima. If in your graph you have multiple maxima or multiple minima, then you cannot apply gradient descent. It will be difficult to gradient descent to find the minima. This is the concept. For example, let's suppose in this graph, which is non-convex graph, suppose I'm applying this process, gradient descent process. Okay, let's suppose. Okay, suppose I started from here. Because in gradient descent, we start from any point. We just initialize our weights and we start from any point. Okay. So let's suppose I start from this point. It will start coming, it will come here, it will come here, it will come here, it will come here, and maybe it will come here at this point. Okay. And then it will assume that it got the minima because suppose I did 1,000 iteration. Okay. And through the gradient descent, I found that this point is minimum. I got this minimum point. So they will assume that this is the global minimum. So the error, the cost function, the error will be minimum here. But actually, this is not the case. So gradient descent can get us stuck in case of non-convex curve, where they have a lot of minima. Gradient descent process get us stuck. They're not able to find the exact, this is the exact point. It will never come. I mean, your gradient descent will never come this point, which is the actual point. It will stuck here. So this is called valley. Okay, in terms of machine learning, we call it valley. It has a multiple valley. This valley, this valley, this valley. It has multiple value. So in order to find the minima, it will stuck in just one valley, but it will never reach to the real value. Where is the real minima? So this is the limitation of gradient descent process. Any doubt here?
What I got it, like so gradient descent is the mathematical way to find the like global minima. Okay.
Yeah.
And it work on the convex graph only.
Yes.
Where there is a only single global minima or maximum.
Yes.
There.
Yes. Yeah. So this is the limitation of gradient descent. It worked very good, very wonderful at the this kind of graph, where it's a convex graph, where it's just one minimum. Okay, your graph has very smooth graph. It has no much valleys like this. It has just one minima or maxima. It will work very well because it will find the minima and will not stuck. But in the multiple valley, it will stuck in some of the valley, and it will never reach to the real minimum. Because this gradient descent is an iteration, right? We did multiple iteration, and at some iteration we find that it's a minimum. We find the cost function, and we assume that we got the lowest cost function at this point because of this iteration, and we assume that this is the real cost minimum cost function, minimum cost value, which will not happen in the non-convex graph. So this is the basic concept of gradient and convex graph.
So this, like coming to our business question, like
yeah, I'm not. Well, by the way, this point is clear. This concept clear.
Yeah, I am clear.
Now I'm coming to the main question, that why we don't use mean square error in case of logistic regression. So my main question, which I want to answer in this video, is why we don't use mean square error in case of logistic regression. Okay. So before coming to that point, I wanted to establish these concepts. I hope this concept is clear, right?
Yeah.
Now. Okay, now let me, okay, so in order to prove in order to show you that why we don't use MSC in case of logistic regression, okay, so this is the statement I'm making, okay, you can just make a statement, make a note. If you apply MSC, mean square error, in case of logistic regression, okay, your cost function, the graph of cost function will be like this, non-convex graph. So this is the concept. If you apply mean square error in case of logistic regression, the graph of cost function is a non-convex. Correct?
Yeah.
And if the graph is non-convex, then you cannot apply gradient descent to find the minimum value. So let's suppose I'm applying mean square error in logistic regression. I'm applying the gradient descent process. It will never give you the minimum value because it can stuck in some value in some valley, and your gradient descent process will never reach to this point, which is a real minimum value. So your cost function will be not optimized. If you're using gradient descent and you're using mean square error in logistic regression, your cost function using gradient descent will be not minimized. So that's a problem with the mean square error in logistic regression. I will show that, okay? But for time being, just make a statement, just make this concept. If somebody asks in interview, if we apply mean square error in logistic regression in sigmoid function, the resulting graph of cost function is always non-convex nature. And because it's a non-convex nature, it is not possible to apply gradient descent because it has multiple values, multiple local minima. And because of that, gradient descent is stuck in some valley and it will never reach to the real minimum value. This way, our cost function will be not optimized if we apply the gradient descent, and this is the reason. In case of linear regression, okay, your cost function always is a convex graph. Now come to the linear regression. What happens in this, everything, I'm just telling the concept, I will prove you right now, okay? So in the linear regression case, if we apply the mean square error as a cost function, so the graph of cost function will be always a parabola like this in case of linear regression. So if it is a parabola, because it has just one global minima, it is easy to apply a gradient descent in case of linear regression cost function. Any confusion in this concept? I will prove this. Okay, just make this statement, these two concepts. Okay, so are you okay with these two concepts? Did you able to get it? I will prove that right now.
Yeah. So second statement is like
Second statement was that in case of linear regression, okay, if you apply the cost function using MSC, your resulting graph of cost function is always a parabola or convex like this, the first one.
Yeah.
So this is a statement, this is the principle. Okay. Now I'm going to prove it. Any question here till now?
No, it's clear. Pretty much clear.
For in order to prove this, what I'm doing here, I'm using ChatGPT. Okay, everything which I explain you, I will use ChatGPT. I'm giving some prompt. Okay, and with the help of ChatGPT, I will explain whatever I made the statement right now. I will explain you with the help of ChatGPT. Okay, so let me share my ChatGPT. Can you see my ChatGPT?
Yeah, I can.
Okay. So here I'm writing a prompt. You can just make a note of this prompt, okay? So I'm writing this prompt, explain this detail. MSc in logistic regression. I made a statement, right? I made a statement that if you apply MSc in logistic regression, it will give you non-convex curve, right? This was my statement, right? So the same thing I'm writing here, explain in the detail, MSc in the logistic regression leads to non-convex cost surface, especially in the multi-feature settings. So what I establish the concept, same thing I'm asking ChatGPT to explain in the detail. Okay, let us see. So here I'm applying MSc in logistic regression, okay, to find my cost function. Okay, so this is my cost function. This is my sigma function, right?
Right.
And it is finding the mean square error. Okay, so this is the error, right? Y predicted minus Y actual whole square and summation. This is the cost. This is the cost function.
Yes,
right?
yes.
Okay. Now, so Y predicted is this, right? 1 by 1 plus
Yes,
E minus theta minus Y actual ka whole square summation. This is my cost function. Okay.
Yes.
So in this here, I'm applying the MSc for my cost function. Okay. So what is the problem with this equation? Right. So this equation is a non-convex. If you apply MSc and try to find a cost function, this function gives you non-convex kind of graph. Okay. So a lot of details. So it has a lot of humps, a lot of local minima. The same principle I explained you. Okay. And it has a problem. It's a convex. Okay, no. Okay, it is applying to multiple features, theta 1, theta multiple features. So it will be okay. So here what I'm trying to establish the concept that if you apply MSc, okay, you will get this. You will get this this function as a cost function. And if you try to draw the plot or graph of this function, it will give you non-convex graph, which I explained earlier. Okay. Now I want to draw this graph. You really want to see in a picture, right? That
Yes.
this is the mathematical equation. I want to see in the visualization that how this graph look like. Okay. So it is giving information that this function is non-convex. I really want to see the graph, how it look like in the space. So for that, what I'm asking here, okay, I'm asking here, draw the 3D graph of MSC loss function in logistic regression. Okay, so let us see how the graph look like of loss function if we apply MSC in logistic regression. Mathematically, you can draw the graph. Otherwise, you can take help of ChatGPT. It will draw a graph for you.
About drawing facility is available on free chat.
Yeah, it has available. It will use PyPlot internally. It will use NumPy and PyPlot. So this is the graph, okay? So 3D graph of MSC loss function in logistic regression, okay? It has a curve ridges, multiple local minima, and it has shape makes optimization using this shape makes optimization using gradient descent tricky and less reliable. I told right. Gradient descent you cannot apply this kind of graph where it has a lot of local minima. So unlike it has it is not convex. Okay, and you can see the code. So basically, it is drawing it is using PyPlot and it is using some library to draw this graph. Okay, so here just try to see this graph. Okay, it has a lot of values. It is in it is in the 3D dimension. Okay, so it has multiple values. So it has a multiple local minima. You're getting this? It is not a smooth bowl or parabola type of graph. There is a multiple minima. So okay, so that is why, because it has a lot of local minima, it won't be possible, or if you apply it, you can apply gradient descent, but it will not give the reliable answer. It will stuck in one of the value, as I explained in the earlier graph.
Yeah. And one more thing, I have one question here to the interviewer asked. Yeah, actually, this is a gradient descent is a very hot actually question.
Yeah, it's a technique. It's a very optimization technique.
Yeah. So he asked me, tell me the graph, like if you between which and which gradient descent graph is forming, between which like x-axis and y-axis. What is appearing on the x-axis and y-axis? Explain.
Now, in interview, they will ask you to generally, first of all, they will ask you draw what is the cost function for any algorithm. What is the cost function? Okay, and if this is a cost function, we can apply the gradient descent or not. So gradient descent, how to apply that? It's a algorithm. I'm not going to cover right now. Maybe
Yeah. So no, the thing is now basically he wanted to ask me. Let's assume that global minima is the like combination of some x and y axis crossing point, right? Common points. That global minima is one point between the x and y axis. If you talk about in the 2D graph, right? So, but what is that meaning? Like that, what is the x axis and y axis basically? Given.
Where in here in this graph?
Not in this graph, like in our original graph, what we were discussing now.
One second.
There.
Okay, let me share. Okay, one second.
So basically, I
Okay, you're talking about this one, right? This picture.
Yeah, see, this global minimum, this P
Hmm.
point,
Hmm.
the one combination of X or Y, right?
This will be, yeah, it will be in x-axis because it is a 2D graph. Okay, so it
Yeah,
will
yeah.
be
So that's
x
why
and
he
y.
was asking, what is the X things here and what is the Y things?
Okay, so x is my, yeah, y is my cost. This vertically, I'm representing my cost. Okay, and x is my iteration. मतलब मैंने कितना iteration किया? Suppose because I'm starting. Suppose 1 second. Let me draw this. You're talking about this, right? Vertically, right?
Yeah,
Like this.
yes, yes.
Like this, right? Yeah. So in gradient descent, see, you are applying the gradient descent on what function? Cost function, right? You're applying the cost function, right? So cost function is क्या? This cost function, for example, in case of linear regression, this cost function has two dependencies, theta naught or theta one, right? Suppose in case of suppose your line is mx plus c. This is your hypothesis, like for linear regression. Okay, so this is depending upon two variables, m and c. I need to find what can be the m or what can be the c where my error is minimum. So it is depending upon two values, theta 0, theta 1. Okay, so here this y-axis, because I'm applying the gradient descent on my cost function. Okay, so this vertically is my cost. This is representing the cost. What is the cost here?
Right.
And x-axis represent your iteration. आपने कितना iteration किया? How many times you did the iteration? Because gradient descent is an iterative process. We do a lot of iteration. Okay, let's suppose I start from here, then I will come here, I will come here, I will go to multiple points, 1,000 to 1,000 point. Okay, like this. So let's suppose I reach here at this point. Suppose I find at this point I found that my cost function is very zero, or like this. Let me grab like this. 1 second. Actually, your gradient descent will be like this. Let me draw the real picture.
And he talked about something about weight.
1 second. So your gradient descent will be like this. When you start the iteration, your cost, this is my cost. Okay, the cost function, and this is my iteration. Okay, so initially, let's suppose my cost is very high. I mean, my gap is very high. I'm doing a lot of wrong prediction. Okay, so after a lot of iteration, your cost will be maybe zero, very less. Okay, and after some time, after a lot of iteration, it will be almost constant. So your gradient descent will give this kind of graph. So initially my cost is very high, very high, very high. And let's suppose at this point, so suppose this is the 100, suppose this is the 1,000 iteration. Let's suppose I did 1,000 iteration of gradient descent. And at this point, I find that this is the minimum. I mean, this is the minimum cost. And after that, after whatever iteration I'm doing, my cost is almost same. It is not making much impact or much difference. That cost is not, I mean, the cost is almost constant after my 1,000 iteration, right? Then I will assume that at this point, it is giving me the minimum cost, the minimum error. I think this was your question, right?
Yeah, yeah. So yeah, the question was yeah, this one only. So just then after that,
Okay.
I do these research things like what was X axis and Y axis.
Okay. Fine. So here okay. So what okay, in ChatGPT, it was showing the graph, right? 3D graph, right? For MSC, right? So it is like this. It is a 2D representation. So you can see it, feel it. So if you apply the cost function using MSC in logistic regression, it will give a multiple values, and the graph will be like this. So the concept says you cannot apply gradient descent. If you apply, you will not reliable. You can apply. I'm not saying you cannot apply. You can apply, okay, but it will not give a reliable minimum cost function. Any questions? This point is clear?
Yes, yes. gradient descent, I was also like, I was not clear with the gradient descent concept earlier.
Okay. Now, so this is the concept I try to establish right now. If you apply the uh, MSC in case of logistic regression, then you will not get a convex graph, and your gradient descent approach will not give you the optimal cost function. This is the problem with the MSC in logistic regression. Okay, so what is the solution for that? So solution is that instead of MSC, we use a log loss function. Log loss. Okay, I'm not going to cover in that. So if you apply the log loss in logistic regression to find the cost function, it will give you a convex type of graph. Okay, and here you can apply the logistic gradient descent. So I'm asking the same thing I'm asking here. Give me the detail on this. So let's suppose I'm applying log loss in logistic regression. Then give the full detail. So log loss in logistic regression leads to convex cost surface. Okay. So this is my sigmoid function. Okay. And here, this is the log, this is the important concept, log loss. So instead of MSC, I'm applying, this is my cost function. So this is the mathematical equation of cost function using log loss in logistic regression. You should know this mathematical equation. Okay. So this is the actual value y, and y, this is the predicted value. So we multiply actual y into log of predicted y like this. So this become my log function. Okay, so we apply this function, then it will give me a convex graph. Okay.
Yeah.
So it has just one global minima, just like so this is the okay. If you apply log loss, it will give a convex graph. In case of if you apply MSC, it will not convex. Okay, in log loss, it has just one global minima. It has many local minima. Okay. Draw the graphs. Let me see the graph. In case of log loss. So it is very smooth type of parabola type of graph. It has just one global minima in case of log loss function. So here you can easily apply gradient descent technique to find the global minima. So it is more reliable. So what I'm trying to say here, in case of log loss, if you're using log loss as a cost function and you apply the gradient descent, your cost function will be more reliable. You will find the real minimum, because the whole purpose of all the model is to minimize the cost function. The more you're able to minimize, your model will be more predictive and more accurate.
Yeah, in another way, actually, now I am able to recall some concept about this log loss function. I understood this concept in another way. There is one question. There is one question on this.
Okay.
There is already sigmoid function in the logistic regression. Then what is the need of the log loss function? The way of question was like this.
Yeah, because to minimize the cost function.
Yeah. Now I can see the answer was like that only. I have remembered because of the sigmoid functions. Basically, sigmoid functions do one thing. It calculates the prediction probability for the actual value. Okay. Either if I talk about the classification problem, logistic regression, so it will predict either yes or no based on the threshold value. Okay. Let's assume if the threshold value is the 0.5, and the prediction probability calculated by the sigmoid functions, that is the 0.75, which is greater than 0.5, right? More than 50%. So it will make the guess. Guess means
No, yeah. So here it is called threshold. For example, 0.5, it's my threshold line. Okay.
threshold
So
line.
if anything is beyond that, that becomes to class A. If anything
Yes,
below that, it's become the
class.
class B.
Yeah,
This is my
yeah.
assumption. Okay.
Yes.
Because the value, the sigmoid function, it will give only two value, either
Yes.
0 or either 1.
It calculates it predicts the probability.
It's give a probability.
It gives the probability value.
Yeah.
So now came to this log loss function where I have remembered this concept. Whatever the prediction is done by this sigmoid function, what log loss function do after that? It validates the accuracy. It validates the prediction of the, like it validates in which way, like how efficient this sigmoid functions predicts the probability, calculates the probability. That is the also that is the also same things with the cost function, right?
Hmm.
So I was not able to like consolidate all these concepts. Now I came to so much
No,
stronger
let's suppose you, because these all algorithm are used by, let's suppose you're using sklearn algorithm, right? So in the library, behind the scene, logistic regression use this concept, a log loss function to get the best fit line. Let's suppose you're writing your own algorithm and you're using MSC to find the cost function. Okay. So your model, though you will find the minima, but your model will be not, your model will be not good because it will give a lot of misclassification. It can be a lot of errors.
Right.
So your accuracy, if you apply whatever like precision, recall, accuracy, whatever metrics we use, it will be pretty bad if you use MSC. Okay, that is why we
See
use
here,
log loss.
in the graph, I was talking about these things only. You can see here. Actually, I learned about these things. The in x-axis of the graph now, there is two values. Either bias or weight should be available on the x-axis. See in the graph.
Yes. Yeah, this is the cost function graph. This is not the gradient descent graph. ये cost function का graph है. If you apply a gradient descent on this, okay, and you will do multiple. So here in the gradient descent, what I do? We are doing a lot of iteration, okay, and we finding the cost. For each iteration, I'm finding the corresponding cost. This is the process of gradient descent, right?
Yes, yes.
We are doing iteration, we're finding a cost. Second iteration, what is the cost? Third iteration, what is the cost? So every iteration, we find a corresponding cost. So if you draw a graph of cost versus iteration,
Oh,
so then
versus iteration.
then that's a gradient descent graph. Okay, कि actually जो आपका gradient descent है, कितना cost किया, कितना iteration किया. So I just want to draw visually. So that's a different thing. This is the actual cost function graph. Let me explain that. Okay, let me explain 1 second. Let me explain with the graph. I think you are mixing two different things.
Yeah.
Let me share my whiteboard. Okay, can you see my whiteboard?
Yes.
Okay. So let's suppose I'm giving simple example. Suppose I'm solving linear regression, simple one. Okay, I'm solving a linear regression problem. Okay, let's suppose. Okay, so in linear regression we have a cost function. I know what is my cost function first of all. There are two things. Okay, one is the cost function. So the cost function will be look like this parabola type. This is the cost function. Okay. One thing. And the linear regression, the hypothesis of linear regression is what? A straight line.
Straight line.
Right? So y is equal to, I can say y is equal to mx plus c. Or y is equal to m is a weight. We can also write like theta 0, theta 1 like that. Okay.
Yeah, we can.
So linear regression. So linear regression is nothing but the linear relationship between your x and y, right? This is your x. X is multiple features.
Multiple features, yes.
And y is your label output, right? So let's suppose here I have multiple point, this point, this point, this point. I have multiple point, right? And I can draw a line. Okay. So this line, okay. So y is equal to mxc. It represents the linear regression. It's a hypothesis. Okay. So all linear regression can be represented by straight line because it's a linear relationship. That's why it's a straight line. This is clear?
Yes.
Okay. Now, cost function, it's a different thing. Cost function का purpose क्या होता है कि how to find this best fit line. I mean, how to minimize a gap between the predicted value and actual value. So for that, the cost function of linear regression is a parabola, quadratic function. That's a different thing. Okay. So the cost function for linear regression will be graph like this, which is a parabola. This is the cost function graph.
Yes.
This is not the linear regression graph. Okay, it's the cost function graph, which is y predicted minus y actual MSC. This is MSC graph. Square summation. So the MSC graph is nothing but your cost function, which is parabola. Clear?
Yes. Yes. Yes.
Okay. Now what you're confusing here, you're confusing with the gradient descent. Okay. So now what next I want to do, I want to find this represents my cost function, right? This parabola represents my cost function. This represents my cost function. So in order to make a good model, we need to minimize my cost function. This is the mathematically we need to do, right? If suppose agar mera cost function bahut hi bura hai, I'm not able to minimize, your model will be not good. It will not give a good prediction. So that is why anyhow, whatever cost function I have to minimize it. And if your cost function has a graph this, okay, it's a parabola. So where I can find the minimum value at this point?
Yes.
Okay. So at this point per, what can be my M and what can be my C? So for that, we apply gradient descent technique. वो कैसे काम करता है? We take any point on this graph on my cost function. One thing, gradient descent always work on cost function, not on the real hypothesis. ये y is equal to mxc पर काम नहीं करता है. Your gradient descent applying on the cost function.
Cost function.
Okay. So his cost function may be take any point and we start moving. We take a lot of iteration. Let's suppose I took 1,000 iteration. Okay. So in order to reach here, I took 1,000 iteration. So pala yahan hua, second, third, fourth, like this, I will do multiple iteration.
I got it.
Now and we have some learning rate. We take some rate. I mean, rate is how much you take the jump from this point to this point. Kitna aap jump kar rahe?
Correct. Learning rate is nothing but that is the
jump
steps. Number of steps defined.
How many steps you're taking between 2 points? Okay, so we apply learning rate, okay, and we reach to this point and we do some iteration. And at this point, if it is a minima, your cost function become almost zero or minimum. So I can say that at this point, my cost function is minimum.
Correct.
Okay, and if whatever iteration I did, I really want to plot somewhere. I really want to see it. Okay, so for that, what I will do, because here this formula, this gradient descent, it is giving you two things. Okay, one thing, it is giving you cost function. What is the cost function value for every iteration, right? Yeah. For iteration 1, what is the cost function value? For iteration 2, iteration 3, like this. So this I can draw a graph plot, okay, to just visualize how my cost function is behaving with respect to multiple iteration. So y-axis is your cost function, cost value, what is the cost, and x is the number of iteration. Okay, so generally the graph look like this. It shows that initially your cost function was very high. But after, let's suppose this point is 1000. Okay, so I can say that at 1000 point, after 1000 iteration, my cost function got reduced. And after this point, my cost function is almost constant. So this is my iteration. And at this point, you will find M and C. At this point, because you are trying to find MSC, जो भी उसका weight है. Okay, so this is the things. You got now?
Yeah, I got it.
So this is your real algorithm. This is your cost function, and you're applying gradient descent, and you will do multiple iteration, and ultimately you have to find the minimum cost, and the value will find, then your model will be more accurate. So this way we train our model. See all the training part, we all training the model. And after that, if you have trained, then we have a lot of matrices, right? Accuracy matrix. So there are multiple things. We apply that, whether it's a real accuracy taken.
So that point should be 0, right? That minimum.
Which point?
That minimum point, global minimum point.
नहीं, cos 0 नहीं होगा. It's a minimum.
Okay.
अगर cos 0 हो गया मतलब कि there's no, I mean, it's 100% accurate, right? Your predicted value and actual value is a 0. There's no gap. You're not a god. You cannot predict 100%.
Yeah.
It's a machine learning. It's not a god. So cost will never be 0. It never comes to 0. It will come minimum. Let's suppose
only tangent will be 0, no? Tangent will be 0.
Slope, yeah. Mathematically, what it does, it is actually drawing a lot of slopes here. Like one slope, this slopes. And ultimately, if the slope becomes 0, it finds that it's the minimum value.
Oh, I got it. At slope, if the slope value will be 0,
yes,
then at that point, the whatever that weight should be like cost
MS.
value will be
yes,
that
will be minimum. It will not become, cost will never become 0. In machine learning model, cost will never become 0. It can't go medium.
Cost means 0 means 100% predictions.
100% prediction, which is not possible. Okay, so I hope you got the concept why we don't use MSC in logistic regression. We always use log loss function. Okay, and this is a very basic concept of all machine learning model algorithms. This is a basic fundamental. You take any algorithm, they all work on this way.
So it means all supervised machine learning algorithm, whatever the available, that follow this gradient like a cost function and gradient descent concept.
Yeah. Yes.
Right.
Now other models, that it is not. I can say that every
supervised. I am talking about supervised.
Right. Every is using gradient descent to find the cost function. They can use the different techniques, but whichever algorithm using gradient descent, which are based on the gradient descent technique, these are concept is almost same for all algorithms. So logistic regression use gradient descent, LR use regression.
Linear regression, logistic regression, gradient descent.
Yeah. So I hope you got the concept. Okay, that this is what I wanted to prove here and show in this video, that and we never use MSC to find the cost function in logistic regression, because your graph will be not convex and it will be difficult to find the global minima. Your cost function will be not minimum if you apply the gradient descent. Okay, so this is the basic difference. I hope you got a lot of value from this video.